Let's talk about the factors that do favor Sn2 reactions. In the previous video, we discussed the proposed mechanism that explains the course of an Sn2 reaction. And in an Sn2 reaction, you have the nucleophile beginning to attack the electrophile, partially forming a bond. All the while, the leaving group begins to break its bond. And this ultimately leads to formation of your new organic product and your leaving group. The idea here is that if you have better nucleophiles, you're going to have a faster reaction. And the reason this ultimately is the case is because a faster reaction is equated with having a lower activation energy. And just remember, this red line up here that goes in the vertical fashion represents the activation energy, the distance from the reactant to the top of the hill. So for you to decrease the activation energy, technically speaking, the way you do this is by raising the energy of the reactants. So technically speaking, whenever we say that we have a better nucleophile, what we're saying, if you pay attention right here on the left side, is that that energy of reactant is going to be raised, because raising that energy of reactant decreases the overall distance to the top of the hill. Anytime that you decrease the value of the activation energy, you have increased the rate of the reaction. So better nucleophiles are those that are technically less stable. Okay, so let's think a little bit about this. Because when you dissolve a salt, you have a cation and then you have an anion. If you dissolve a salt in a solvent that is protic, in other words, a solvent that contains OH bonds, NH bonds, technically HF bonds, but technically that would be a different type of solvent that you might want to avoid if at all possible. That's quite toxic and dangerous. But if you do have a solvent that has OH bonds or NH bonds, this is what we consider a Aprotic solvent. And in those particular solvents, you end up forming coordination compounds along the cation, but also technically around the anion. And the idea is that the partially negatively charged of the solvent coordinates to the metal cation. The partially positively charged portion of the solvent interacts with the lone pairs of the anionic fragment of the ionic substance. So you basically, by surrounding the anion with this partially positively charged species, you're stabilizing that anion. So solvation in Aprotic solvents is not going to help you. You're stabilizing the anion, which means that you're going to lower the energy of the reactants, and that will mean that the activation energy is larger. So this will actually slow down the reaction. So for you to come up with a better nucleophile, yes, and then you lower the you lower the energy, making the activation energy larger. So for you to make this a better nucleophile, you kind of have to switch things a bit. But before I get to that, one specific case that I want to highlight is that of the halides. When you use halides as nucleophiles, the idea is that in Aprotic solvents, yes, the cation is going to be coordinated, covalent and coordinated by the solvent, while the anions are going to be interacting with the hydrogens of these positively portions of the molecule. And that's going to be true for fluoride, chloride, bromide, and iodide. But the thing is that fluoride is the smallest out of the halogens, and as such, it has the greatest electron density. The size per charge is the greatest for fluoride, and so the interaction with the partly or partially positively portions of the solvent molecule with the fluoride is going to be a lot higher than it is for chloride, which itself is going to be higher than it is for bromide, which itself is going to be higher than it is for iodide. So in this particular framework, iodide is going to be the one that's going to interact the least with the solvent, and as such, iodine is actually the one that's most available to attack electrophilic substrates. Whereas fluoride is basically completely locked in place by the solvent and makes it very difficult for fluoride to reach over to the electrophilic carbon. So you have this order. So in Aprotic solvents, iodide is the better nucleophile than any of the other halogens, just because all the other halogens are trapped by the solvent in the solvent cage. But if you change the pictures, and specifically if you pick a solvent that doesn't have OH bonds or NH bonds, you are dealing with what we call an aprotic solvent. And the idea with aprotic solvents is that you can no longer stabilize the anions. If you look at this right here, once again, having that OH or NH bond creates that delta plus that interacts beautifully with the anion. But if you get rid of an OH or NH bond in your solvent and you don't have it to begin with, then that interaction basically cannot happen for the anion. So you basically leave the anion naked. And because the anion is naked, it doesn't have solvent stabilizing its charge, you have in essence raised the energy of the reactant, of the nucleophile. And this makes the reaction go faster because you have artificially reduced the distance of the activation energy. So in essence, aprotic solvents are key aspects of your Sn2 reaction. And typical solvents are the ones shown here. Acetone is a typical aprotic solvent. You do have oxygen, but notice that there is no hydrogen bound to it, so this is aprotic. DMSO, which stands for dimethyl sulfoxide, it's also a good solvent that's used quite often. Aprotic, has oxygen, but it does not have hydrogen directly bound to oxygen. And then acetonitrile, that's another typical aprotic solvent. Does have nitrogen, but the nitrogen does not have a bond directly to hydrogen. So these are your typical aprotic solvents. And typically we abbreviate dimethyl sulfoxide as DMSO or acetonitrile as MECN. Those are the typical abbreviations. Other typical solvents are DMF, dimethyl formamide. We have tetrahydrofuran or THF, which is an ether. And another solvent that can be used depending on the condition. Sometimes this is not a good solvent to use in substitution reactions, but in some mild ones you can use like chloromethane or DCM, also known as methylene chloride. The last set of solvents that you could use that also qualify as aprotic are diethyl ether, dimethoxyethane, which is technically a polyether, and chloroform, which has an extra chlorine compared to dichloromethane. All right, so any of those solvents can be used to basically yield a naked anion. And when the anions are naked in the halogen series, fluoride, which has the greatest electron density, is the better nucleophile. Right now, iodine is the poorest. It's always been the poor nucleophile, but because in the previous example with the Aprotic solvents, it was surrounded the least by solvent, it was the one that could access the electrophilic carbon the best. But right now, in the absence of that solvent cage, fluoride is the champion. Fluoride will be the one that will absolutely win at attacking that electrophilic carbon. This is of course only in the halogen series, right? So don't think that fluoride is the best nucleophile of them all. It isn't. But in aprotic solvents, if you're just doing reactions with halogens, fluoride is the one that's going to win. If you're doing the substitution reaction in protic solvents, iodide is the one that's going to win. Okay. So that kind of brings us to the idea of the substitution of the electrophilic carbon. The more bulk that you present around the electrophilic carbon, the more difficult it is for the nucleophile to reach over and form the trigonal bipyramidal intermediate. And the way we represent this is just by saying that the activation energy of this transition state is going up. You're actually increasing the activation energy by raising the transition state energy. All right, so the reactants remain at the same level, the products remain at the same level, but the activation energy increases when you go from primary to secondary to tertiary as a result of the increased bulk that makes it harder for the nucleophile to reach over. So you're destabilizing the transition state and slowing the reaction. By the time you get to the tertiary alkyl halides, you have slowed down the reaction to such an extent that by all intents and purposes, the reaction doesn't happen. And that's what I want you to take away from this particular slide. Sn2s are never going to happen with tertiary electrophiles, no matter how much you try. And even in cases where people try to make it happen, other reactions take place instead of the Sn2 reaction. So keep that in mind. Secondaries, we can make it happen. We're going to talk about the conditions in a little bit, which favor Sn2 reactions for secondary alkyl halides. Primaries are definitely good for Sn2 reactions, as well as methyl halides. Okay, now let's take a look at the leaving group. A leaving group, no matter of whether you're dealing with an Sn1 or Sn2 reaction, you're always going to want to have a good leaving group. And a good leaving group is one that derives from a strong conjugate acid, right? Now, to have a good leaving group means that you are going to make it easier to break this Rx bond. And if you make that easier to break, you are lowering the transition state energy. So lowering that top of the hill automatically lowers the value of the activation energy, which in and of itself makes the reaction go faster. So you definitely want to have good leaving groups, in addition to having good nucleophiles, in addition to having a Aprotic solvent. So if we want to put all of that together, the table that describes what favors an Sn2 reaction says that the substrate, and this should be the first thing you look at when you're trying to assess if a reaction is going to go via the Sn2 or Sn1 route. The substrate has to be either methyl or a primary alkyl. In some circumstances, secondary alkyls can definitely behave as an Sn2s. In particular, if your if your solvent is aprotic, that's good. That's probably gonna help out your secondary alkyl molecule to undergo an Sn2 reaction. And generally speaking, the solvent is kind of gonna be the key player to look at in terms of making that assessment. The nucleophile, you want it to be as good as possible, a gap. And of course, a leaving group, it better be a good leaving group. And if you don't have a good leaving group, then you better have a method of turning that bad leaving group into a good one. And we talked about some of those things before. You can use sulfuric acid, HCl, to turn that bad leaving group potentially into a good one. Okay, now I'm going to show you two examples of reactions that you can assess as being Sn2 or Sn1. And in this case, we have a secondary alkyl tosylate. Now, tosylate is a good leaving group. Now, I already mentioned that this is a secondary alkyl halide. Tosylate, we said, is a good leaving group because it derives from a strong acid, tosylic acid, which has a negative pKa. The substrate is being combined with sodium cyanide, and cyanide is not only a good nucleophile, it's an excellent nucleophile. So that's already looking good for an Sn2. Now, the thing that absolutely makes it clear that this will be an Sn2 reaction is the fact that you are using DMF. DMF is an aprotic solvent. You never have oxygen bound to hydrogen or nitrogen bound to hydrogen. So this is aprotic solvent with good nucleophile, with a good leaving group, and a secondary alkyl halide spells out Sn2 reaction. So what you would do is carry out the Sn2 reaction. Now here, notice, however, that the electrophilic carbon, is technically chiral. So you have to pay attention to that bold bond, because the moment the cyanide group attacks via an Sn2 reaction, the configuration of that bold bond is going to change. In fact, all you really need to do is change it, but I'm going to show you the mechanism. The cyanide attacks this electrophilic carbon, and the tosylate group takes off. And so you end up forming the opposite configuration for your final molecule. And if you look at the configurations via, they have Newman projections. In this case, looking at it from the opposite view of the the opposite view of the lowest priority group, which is the hydrogen, we see that tosylate is to the left, ethyl groups to the top, and methyl groups down into the right, which is what we have here. Over on the product side, opposite of the hydrogen, we have methyl down, cyanide to the right, ethyl group to the left. Priorities, oxygen is higher priority than carbon, and between ethyl and methyl, ethyl is the higher priority, so you have priority 1, 2, and 3. Follow that order and you have an R configuration. Over here, between ethyl cyanide and methyl, cyanide is the higher priority simply because you're bound 3 times to a nitrogen through that triple bond. Ethyl is higher than methyl, so you have the following sequence, and if you rotate in that direction, you find out that this is the S configuration. Now, as I said, depending on the identity of the nucleophile, you could start with R and end with R. That doesn't mean that the configuration hasn't changed. All it means is that the priorities of the groups, were not exactly the same. So just be aware of that. But right here, we did have a proper inversion of configuration. Not only do we get the umbrella to change places, right? This was pointing up and to the right. Now it's pointing down and to the left. But we also have R turning into S. Okay, and the last example that I'll show you is one with cyclohexanes. In particular, cyclohexane that has the sec-butyl group and methyl groups nearby this bromo group. Now, in order to make sense of this, first things first, notice that you have a good nucleophile. Notice that this is a secondary alkyl halide, and so is that one. You have an aprotic solvent. This is spelling out Sn2 reaction. So the way to do this is you have to draw the actual chair conformations. And notice that the bromine as well as the sec-butyl have bold bonds right here. So that means that they have to be above the hydrogen. So if I place the bromine over here, the bromine is above the hydrogen. Over here, the sec-butyl is above the hydrogen. The methyl group is part of a dash bond, so it has to be below the hydrogen. And the blue molecule right here that is technically a diastereomer of the first molecule that we presented is going to be kind of similar, except that the bromine is going to be should be below this thing, right? All right, so here it is. So we have the bromine below the hydrogen in the blue scheme. What I'm drawing right here is the actual two chair conformers that show up, right? So in this case, the bromo group is axial. In that case, it's equatorial. And right here for the blue chain, we have the bromo group below the hydrogen, and the conformer has the bromine still below the hydrogen, but now before it used to be axial, now it's equatorial, right? So if we look at this, the idea is that when you bring your nucleophile, we're going to have to make a judgment call as to which one of these two is going to react faster. So notice that for the more stable conformers, and we're saying that these are the more stable conformers because the biggest group, the sec-butyl group, is in the equatorial position in both of these chair conformations. So these are going to be the most predominant species in solution, the species that the nucleophile is going to interact with the most. So what you see here is with the most stable versions of the chair configurations of those two molecules, when methylphthalate comes in to attack, it has to attack from the opposite end of where the leaving group is located. So if you have the leaving group in the equatorial position, the nucleophile has no choice but to attack from this inner face of the cyclohexane ring, which has severe interactions, steric interactions with the diaxial bonds down in the cyclohexane chain. And so this is not a good situation. On the other hand, if your bromine is axial, well, the nucleophile can attack from the top, and it doesn't really encounter too much friction from these axial bonds because now it's coming off at an angle. It's not exactly being jammed in there. And so this works a lot better. And so the end result is that, yeah, you could draw the products that you're going to get from these two outcomes, but really out of the two, the one that's really going to become the major product in your reaction is the one that makes it easier for the nucleophile to access the electrophile. And that's the one in which the leaving group is on the axial position of your cyclohexane molecule. All right, we're going to stop right here, but on the next video, we're going to start talking about the conditions that favor Sn1 reactions. So I'll see you then.